Hi students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as magnetic effect of electric current. Now before we actually start with the chapter, let's just recap a couple of basics that we've already done. Let's see this. Let's consider that if I have dl, the length of a small element of a conductor carrying current I. If dl, start writing guys, is length of small element of a conductor carrying current I. Right? Now, if I consider, see this is your conductor, this is dl, small element of the conductor carrying current I. Right? Now, let's also consider that there is a point A which is at a distance of r from the center of the conductor. Point A which is at a distance of r, making an angle of theta. Right? So consider a point A at a distance of r, making an angle of theta. Right? In which case I can say that by Biot-Savart's law, we've learned this before, the magnetic induction at point A due to small length of the conductor dl is mu 0 upon 4 pi I dl sin theta upon r square. Biot-Savart's law said that the magnetic induction at a point is directly proportional to the current flowing through the conductor. The magnetic induction is directly proportional to the length of the conductor, inversely proportional to the square of the distance, and directly proportional to the sine of the angle that the given point makes with the conductor. Right? Now, so this was Biot-Savart's law, which we have already learned. First, I'm going to revise a few concepts of magnetic effect before I move ahead with current syllabus. Next, we had also seen that what will be magnetic induction at a point at a distance A. Magnetic induction at a point at a distance A from an infinitely long conductor. Now in the previous case I had considered only a small element of the conductor from an infinitely long conductor carrying current I. We had found this out to be magnetic induction was mu 0 I upon 2 pi A. This is magnetic induction due to a long current carrying conductor at a distance of A. Next, we had also found out last year, that is when you were in 11th, magnetic induction at the center of a circular coil. Magnetic induction at the center of a circular coil of radius r having n turns carrying current I. In which case I can say that B is nothing but mu 0 Ni upon 2R. This was the magnetic induction at the center of a current carrying coil. And the last thing that we had seen was magnetic induction at a point on the axis at a distance of x. Magnetic induction at a point on the axis at a distance x from the center of a circular coil of radius r was given by the formula B is mu 0 n I r square upon 2 r square plus x square raised to 3 by 2. This was magnetic induction at a point on the axis, right? Then we had also found out the force due to a magnetic induction. By suppose if the length L and current I are placed at right angles, then in uniform magnetic field of induction B, then I can say that F, then the force acted upon them is nothing but BIL. So these are all the terms that we've learned in our previous class, right? Can you just go through them once before we move on ahead? Okay, let's move on ahead now that we've done those basic concepts. So these were the basic concepts of magnetic induction. One, due to a small current carrying conductor. Next, due to an infinitely long conductor, due to a coil at an axis, and the force that is produced due to magnetic field. Right? Now, let us see Ampere law. Now, what does Ampere law state? It states that the line integral of a magnetic field, I'll just explain the law. First, let me write the law, then I'll explain it to you. Line integral of a magnetic field round any closed path is equal to mu 0 times the total current. In the closed circuit. That means, let's assume that I have a conductor. I have a conductor. Let's assume I is the current flowing through the conductor, right? And you have a magnetic field that is produced around here. Let's assume you have a circular magnetic field produced around this part. Now, let's assume that this radius is, say, r. Let's consider this radius to be r. Then the magnetic induction will always be in tangential direction. So the magnetic induction is going to be in tangential direction. This is the direction in which the magnetic induction is going to be. Now, if I consider a small element, this is a small element here, dl. If I consider this small element dl, then the magnetic induction by Biot-Savart's law will be B, and it will be in tangential direction. Now, Ampere law says that in this case, if you have a current carrying conductor, in that case your integral of magnetic induction for any given small element, integral of magnetic induction for any given small element is equal to mu 0 times current. That is what is Ampere law. The integral of magnetic induction, if I integrate magnetic induction for a small element dl, then for a closed circuit it is going to be mu 0 times current. Let's try to understand this further. So this is your Ampere law. Once you have this Ampere law, let us consider that, I'll explain, we'll derive this now. Consider a circular path of radius r carrying current I. You have a circular path which is carrying current I. Okay. Now, in that case, current I passing through O. Right? In which case, let's consider that PQ is dl vector. I said we consider a small element on that given circular path, and let's call it as dl vector. Then the strength of the magnetic field produced at point P, let us assume, is B. Strength of magnetic field at point B is at point P, let's assume, is equal to B. Right? In that case, I can say that the direction of the magnetic field is going to be tangential to P. The direction of the magnetic field is going to be tangent to the circular path at P. Direction of magnetic field is tangential to circular path at P. Right? Therefore, I can say what will be the line integral of the magnetic field at point P? The line integral of magnetic field at point P, integral, right? I want to find out the line integral. That means I want to find out B vector dot dl vector. How do you find out dot product of two vectors? Dot product of two vectors is nothing but the magnitude of two vectors and cos of the angle between them, right? So in that case, I can say this is going to be equal to integral of B dl, and the angle between B and dl is going to be 0 degrees, right? So that is going to be cos of 0. Cos of 0 is nothing but 1, so this is going to be integral of B dl, right? But we have already found out that magnetic induction, at point P but I can say that magnetic induction produced by P is given by mu 0.4 pi 2I upon R. This is the magnetic induction that is going to be produced due to point P, right? Now in that case, substitute this value of B here. If I substitute the value of B here, then in that case I can say that therefore integral of B vector dot dl vector is equal to integral of B into dl. We found out, substitute the value of B, so that is mu 0.4 pi 2I upon R into dl, right? Everything what is constant will come outside the integral sign. So get the constants out. If I get the constants out, you will get mu 0.4 pi 2I upon R integral of dl, right? But for a closed path, integral of dl is going to be nothing but 2 pi r. It's a closed path, so the integral of dl will be the circumference, right? So in that case I can say that but integral of dl is going to be 2 pi r. So in which case I could say that integral of B vector dot dl vector will be equal to mu 0.4 pi 2I upon R into integral of dl. I'm substituting as 2 pi r, right? And if I substitute this as 2 pi r, then what remains is 2 2s are 4, pi and pi is gone, r and r is gone. That leaves you with mu 0 I. That is your line integral. That's how you derive ampere.
No, it is point P.
Point P is here, right? Point P is that point where you have that element dl.
Okay.
Right? So in a closed circuit, the line integral of a given magnetic field is going to be equal to mu 0 times current. Fine, do we understand the derivation? Simple, straightforward law. Now, let's find out the magnetic induction outside a conductor. Now that we know the Ampere law, we could use the Ampere law at various places. Let's use the Ampere law and find out the magnetic induction outside a conductor of infinite length carrying current. Now let us consider xy to be an infinite long conductor, right? Now let's assume that P is a point at a distance of r from the conductor. You have this long conductor. You consider xy to be a long conductor. Consider P as a point at a distance of r from the conductor, right? So you say consider let P be a point at a distance of r from the conductor. Right? In that case, in order to find out the magnetic induction at point P, draw a circle of radius r which passes through P. Draw a circle of radius r which passes through P, right? Such that xy is perpendicular to the plane of the circle. Such that xy is perpendicular to plane of circle. So what we had in the previous diagram. So I'm going to redraw this diagram here to show you the plane of the circle. This is my plane of the circle, right? This is your point P. I'm going to draw a circle here first. I have point P which is at a distance of r, right, from the center. This is your long conductor xy, right? Okay, once you have this, then you can now apply your Ampere law. I can say that the magnetic induction B at point P due to current, here I have current I which is flowing through the conductor, right, is going to, this is your current xy that passes through the conductor. So I can say that let PQ vector be equal to dl and B be the magnetic field and B be the magnetic induction. B be the magnetic induction at point P due to current I. So I is the current flowing through the conductor, B is the magnetic field that is produced at point P. Then I can say that the line integral of the magnetic field in a circular path, line integral of magnetic field in a circular path by Ampere's law, circular path will be nothing but integral of B vector dot dl vector, right? But by Ampere's law, integral of B vector dot dl vector is nothing but mu 0 I. If I apply Ampere's law, this is what I'll get. Now, where mu 0 is the permittivity of the medium. Now let us assume that theta is the angle between B and dl. So in that case, theta has to be 0. If theta is the angle between P and dl, then theta is 0 and cos theta is 1, right? So in that case I can therefore say that the line integral also, integral of dl is going to be 2 pi r, right? So in that case I can therefore say that integral of b vector dot dl vector is mu 0 I. B is constant, comes out. Integral of dl is mu 0. Before this I can write as integral of b dl cos theta is mu 0 I. So this is going to be b is constant, comes out. dl cos of 0 is 1 mu 0 I. B integral of dl is nothing but 2 pi r is mu 0 I. Therefore I can say B is mu 0 I upon 2 pi r. Thus using Ampere law you can find out the current in a straight conductor. Right? Now this can be further written as B is equal to mu 0, multiply the numerator and denominator by 2. So this is 2I upon 4 pi upon r, and that was the current due to a straight conductor. That was the current due to a straight long conductor. Right? Similarly, all your magnetic laws can be derived by using Ampere law. Right? I just derived the equation for this. Yeah, this is the equation that you derived. Where is it from? Yeah. You just derived the magnetic induction for a straight long conductor carrying current using Ampere law. Right? Now I could similarly use the Ampere law and derive all the three laws that we've already studied. Let's try to find out the magnetic induction inside a conductor of infinite length carrying current. Let's try to derive one more law. Magnetic induction inside a conductor of infinite length carrying current. Now, inside, right? So in that case, I can say that consider a conductor of radius r Let us consider a conductor of radius r carrying current I. Right? In which case, I can say that the magnetic field B depends upon the distance of the point from the axis of the wire. I can say since the current is uniformly distributed across the cross section, therefore I can say that the magnetic field B depends on the distance of the point from the axis right. Now let us consider that the magnet, let's try to find the magnetic induction at a distance r. So I can say that magnetic induction at distance r from the center of the wire. Let's try to find out the magnetic induction at this distance. So in that case, you will get this as you have this is your conductor, this is your radius r, and this is the point r which is at a distance. This is the point, given point, say P, which is at a distance r from the radius of the center of the conductor. This is your radius of the circular coil. This is your radius of the circular coil, right, where you have current flowing, current I flowing. This was the initial part, that consider a conductor of radius r carrying current I, right. Now I want to find out the magnetic field at this point P, which is at the distance of r from the center of the coil. Now I can say that the area of the cross section of the wire, area of cross section of wire is going to be nothing but pi r square. That is going to be the area of the wire, right. So in that case you could say that current per unit area, you could say current per unit area is going to be nothing but I upon pi r square. If the area is pi r square, then the current per unit area has to be I upon pi r square. Now let us consider a circular path around the center. Consider a circular path around the center. If I consider a circular path around the center with radius r, right, and let's assume that B is the magnetic induction at this point. B is magnetic induction at distance r. In that case I can say that line integral will be nothing but integral of B vector dot dl vector. That's going to be the line integral of a given point at there. The line integral of a given point on that particular circle will be nothing but B vector dot dl vector, right. Once you have this, then I can say that this is going to be integral of B into dl into cos theta, right. Obviously the magnetic induction and the given point are going to be at an angle of 0, so theta is going to be 0, cos theta is going to be equal to 1, and integral of dl, since you have drawn a circle around the given path, integral of dl is going to be nothing but 2 pi r. Therefore I can say integral of B vector dot dl vector is going to be nothing but, B is constant, cos theta is 1, integral of dl, which is nothing but 2 pi r, so B into 2 pi r, right. Now the current enclosed in this path, current in the closed path, you've drawn this circle of radius r. What will be the current in this closed path? It will be nothing but the current per unit area multiplied by the area of the closed path, right. So in that case, this is going to be current per unit area into area of the path. Current per unit area we already found out as I upon pi r square. Area of the closed path is going to be pi r square, right. So in that case pi and pi gets cancelled, so the current in this path will be IR square upon r square, right. By Ampere's law, if I apply Ampere's law, I can say by Ampere's law I can say line integral is nothing but mu 0 I. Line integral you just found out is nothing but b into 2 pi r mu 0. Current you just found out is I r square upon r square. Thus I can say that magnetic induction is mu 0 I r square upon 2 pi r into r square. R and R gets cancelled, so the magnetic induction is mu 0 I r upon 2 pi r square. Right? So that is going to be your magnetic induction inside a conductor of an infinite length carrying current. Right? We will stop this here for the day. Thank you very much.